Hello, class. So on this video, we'll continue the discussion that we started in the previous video about finding solutions or a fundamental set of solutions to the second order homogeneous ODE with constant coefficients. Right? So we went over this whole argument about why we want to choose a function that looks like y equals e to the rx. So we did all that. And then from plugging that function in, we saw that we got this equation here. Didn't mean to erase, I meant to signal to it. We got this equation, and what that meant was that us finding solutions at the form e to the rx, so this differential equation, was equivalent to finding roots of this polynomial equation in R. So that's where we ended up in the last video. Now I'm going to basically start from here. So starting from here, we have the polynomial equation ar squared plus br plus c equals 0. Now this is a second order, yeah, I guess it's a second degree polynomial equation. Right? As you know, we can use the quadratic formula. So in fact, we can find what the roots are of this equation are just by using the quadratic formula. The problem is we ideally want two roots, right? Why do we want two roots? Well, we want two roots because we're working with a second order ODE, right? So we want from this to get y1 equals some root, r1, which is one of the roots, and we want another solution of the form with the other root, right? That'd be nice, and it'd be nicer if they were linearly independent, but we'll worry about that later. So again, it'd be nice if we could get two distinct roots, R1 and R2, so that we can get two distinct solutions. Now, if you remember from college algebra, which is fine if you don't, but it's not always the case that we're going to get two distinct roots. In fact, there are three possible cases we can get. Right? So before I go into that, let's see what the roots look like. So let's use the quadratic formula. Right? The formula is negative b plus or minus square root of b squared minus 4ac all divided by 2a. So from this we can read the two roots. Right? We can read r1 equals the positive one, so let's use negative b plus, so positive in the sense that the sign there is a plus, b squared minus 4ac all divided by 2a, and r2, I'm going to write it a little bit lower. And R2 being the solution with the negative sign. So negative b minus the square root of b squared minus 4ac over 2a. So these are the solutions that we get from the quadratic formula. However, as I mentioned, it's not always the case that we get two distinct roots. Why? Well, there's three things that could happen. First, everything works out, right? And we get two distinct roots, R1 and R2, as we have here. The second case is that we get one root with multiplicity 2. Right? So remember that that could happen if we had, for example, something that like this. And in fact, this is a good example. Y equals x squared. This has only root. The only root this function has is x equals 0, but it has multiplicity 2, meaning that when it touches the x-axis, it doesn't cross, but in fact, it bounces off. Right? So even multiplicity has this bouncing behavior. Right? So as we can see, it's possible to only have one root. The other case is, so this would be the case of one root, multiplicity 2. Now the other case, what if our function looks something like this? Actually, I shouldn't call it y of x. This is a function of r. Right? So we're working with r as the independent variable. Right? So this is the ry plane. Right? So now what if I have a function like this? Well, this function is not crossing the x-axis, but there are still two solutions. What is the problem? The solutions are not real. They're complex solutions, meaning that they have an imaginary part. So let me phrase that a little bit different. So real solutions are also complex. So let me just say that the solutions in this case have an imaginary part. So two solutions with an imaginary part. So these are the cases in which we're going to have trouble. Again, in the case in which we have two distinct roots, we're good, right? We can just plug them into these equations. However, as we see here, it could be that we have one root with multiplicity 2, or two roots, but they have an imaginary part. And as I mentioned, we only want to work with real numbers here. So how do we deal with these two cases? So that's going to be the focus of the next, couple, maybe more, probably more than one video. So let's go through all the cases. So case one, we have two distinct real roots. As we saw, in this case, we know what the roots are. So let me just write it again. In this case, the roots are So in this case, the roots of AR squared plus BR plus C equals 0 are, right, we just wrote them before, I'm just going to write them again. R1 equals negative B plus square root of B squared minus 4AC over 2A, right? And R2 equals negative B minus the square root of B squared minus 4AC all over 2A. So what happens? Well, we get two solutions. Y1 equals e to the R1x, where R1 is as given, and Y2 equals e to the R2x. Now, these are two solutions. We don't necessarily know that they're linearly independent, right? So we don't know that they actually form a fundamental set of solutions, but we have a tool to check that. We can use the Wronskian. So let's use the Wronskian and see if these functions are linearly independent, and if they are, on what intervals are they linearly independent. So let's do it. Let's go ahead and calculate the Wronskian. So let's do it in a different color. Let's say blue. Let's calculate the Wronskian of y1 and y2, which is the Wronskian of e to the r1x, e to the r2x. So if you remember, you're trying to find the determinant of this matrix, right? So the first column is pick any of the two functions. I start with this, the one with r1, right? Its derivative. And here you start with the second function and put the second derivative, the derivative below it. And then calculate this determinant. So you use, by definition, right, you just take the first diagonal, multiply those entries. So we get e to the r1x times r2 e to the r2x minus, or you subtract the product of the other diagonal. So here we get e to the r2x times r1 e to the r1x. So let's simplify this. So same base, you can add the exponents. So this becomes r1 plus r2x minus r1 e to the, again, same base. So you can combine the exponents. Now we can factor out the e to the r1 plus r2x from both sides. So let's do that. And if we do that, we're left with r2 minus r1 here. Right? And now remember, for these functions to be linearly independent, we want the Wronskian to not be equal to 0. Now, remember that we're in the case where we have two distinct roots. Right? So I didn't draw a picture for this before, but let me do it now. So we get two distinct roots. Right? So an example of what this might look like would be something like this, right? Where this would be R1. Oh, let me use a different color. This would be R1, and this would be R2. So we know we have two roots and they are distinct. R1 is not equal to R2. Why is that important to us? Well, if we set this Wronskian equal to 0, so we have e to the R1 plus R2x times R2 minus R1. And let's see if there are any solutions. Are there any x values that make this equal to 0? Again, if there are any x values that make this equal to 0, we have to get rid of those, right? We can't include them in the interval on which these functions are linearly independent. But, however, notice that since R1 is not equal to R2, we know that R2 minus R1 is not equal to 0. So the only way this would be 0 is if the other factor, which is e to the R1 plus R2 x equals 0. However, again, what does the graph of this function look like? Well, e to the x looks like this. And what are we doing? We're multiplying x by this constant R1 plus R2. So as for the same reasoning as before, all this can do is either reflect about the y-axis or stretch or compress horizontally, meaning that this function or this expression is never equal to 0. There is no x that makes this true, right? But e to the R1 plus R2x is never equal to 0. What does that mean? Well, this is never equal to 0. This is never equal to 0. So the Wronskian is never equal to 0. So what does this mean? Remember, these functions are linearly independent wherever the Wronskian is not equal to 0. So in conclusion, since the Wronskian is never equal to 0, this means that y1 equal to e to the R1x and y2 equal to e to the R2x are linearly independent, which I just write like this, Li for linearly independent, for all real numbers. They're also defined everywhere. We know that there are solutions everywhere, right, by construction, because we started by plugging y equals e to the Rx in, but you can verify again, you can plug them in again, see that there are solutions. So what does that mean? This is a fundamental set of solutions. For the differential equation. And what does that mean for us? Well, that means that these two functions, or that the general solution is any linear combination of these two functions. So any function that looks like this where C1 and C2 are arbitrary. So in the case that we have a homogeneous second order ODE with constant coefficients and these solutions of the polynomial that I mentioned, that in fact it has a name. I don't know why I didn't mention it. I should have mentioned it before. But this polynomial here actually has a name. This is called the characteristic polynomial. So let me give it a name as P of R, so P for polynomial. It's called, and it's important because you'll see this name in the literature. So this polynomial that we get from the differential equation is called the characteristic polynomial. Of the differential equation. So using this language, in the case in which our characteristic polynomial has two distinct real roots, then we can find the general solution. The general solution is just this here, where R1 and R2 are the roots. So in this case, we can easily find the general solution. And again, this is the general solution for all real numbers. Remember, this is on I. So actually, let me make that precise. This is general solution on I equals negative infinity to infinity. So now we know how to solve second order homogeneous ODEs with constant coefficients when the characteristic polynomial, which again is this polynomial here that we started with, has two real distinct roots. So this was the case that we kind of already knew wasn't going to give us any problems. Right? So it works nice. We know how to find the general solution in this case. What happens in the case in which we have one real root, but of multiplicity 2? That's what we're going to see in the next video.